It always takes a moment to get the live stream going. Excellent. Let me get that sorted here. Okay, so thank you everybody for joining us today for this week's Monsoon Seminar Series. We are joined this week by Samantha Bova at San Diego State University. And so just remember that please curate your questions in the chat, basically within the Zoom meeting. And then at the end, we'll basically call out your question, which you can either read aloud or which we can then read for you. So without further ado, Samantha, if you would share your slides, we can learn a little bit more about the Pacific Worm Pool.
Awesome, thank you, Tara. All right, so we'll get those going. All right, so great. So it's my great pleasure to participate in the Monsoon Seminar Series. Today, we'll be looking at orbital scale variability in rainfall in the Western Pacific Worm Pool, looking at our record from this region that spans the last about 2.3 million years. All right, so we'll just jump right in. So we're working in the Western Pacific Worm Pool. Why this location? This region is a zone of extremely warm sea surface temperatures defined by the 28 degrees C isotherm you see here. The consequence of this is lots of warm water at the surface. This is a huge supplier of heat and moisture to the atmosphere, which has global ramifications for atmospheric circulation and also has huge consequences for the region in and surrounding this zone of very warm water. And so what we're going to do is kind of look at kind of what are the main drivers of rainfall and convection in this part of the world, and kind of figure out what we can learn about this from looking at the paleo record, and in particular looking at the response to changes in orbital forcing. But we'll always good to kind of start in the present and thinking about what drives variability in this region today. So this is a map of precipitation in millimeters per day over the kind of Indo-Pacific Worm Pool region. We see that a huge driver of changes in rainfall in this region is the seasonal migration of the intertropical convergence zone, north in summer, south in boreal summer, and south in austral summer, following the seasonal cycle and the maximum sea surface temperature and incoming solar insolation. To the north and south of the heart of the Worm Pool region, we of course have our monsoon systems, Indian and East Asian to the north, and the Australian monsoon to the south. And the interaction between the monsoons and the seasonal migration, the ITCZ, is very important. And in particular during, at present, we see this being a huge source of the total variance in global precipitation today. And so you can see the kind of seasonal cycle in incoming shortwave radiation up here on the right, and then the kind of ITCZ tends to kind of follow this across the seasonal cycle, leading to a north-south dichotomy in rainfall across the year, with maximum summer rainfall in the northern hemisphere corresponding to periods of minimum rainfall in the southern hemisphere and vice versa. And often this paradigm gets applied in terms of interpreting records further back in time as well. Something else that we need to be considering, especially here in the tropical Pacific region, is the impact of also ENSO on rainfall patterns here. And then finally, I'll also note that it's been observed on millennial timescales and also in the modern hydroclimate system. Changes in the width of the ITCZ may also be important. So this is just a data set here looking since 1980 to 2010, and you see, at least in the Central Pacific region, a trend towards a narrowing of the kind of seasonal range of the ITCZ, leading to a contraction, and at the same time you see an intensification within that region as well. So these are all just important things to keep in mind that are controlling rainfall today and may be useful for understanding how rainfall changed here in the past by looking at the response to changes in orbital forcing. And so of course we have changes in precession, which are expected to impact rainfall in this region by either local or regional gradients in insolation. And then obliquity at 41 kiloyear and eccentricity at 100 and 400, having more of an extratropical impact on the tropical rainfall in this part of the world by either the pole to equator temperature gradient, changes in sea level, or impacts by ice volume. All right, so we can look at the response to these different orbital parameters in the warm pool and try to kind of figure out what are the key drivers of rainfall here. And there's been lots of work in this region before. I'll just highlight 3 records from the heart of the warm pool region, 2 from Papua New Guinea, 1 from Borneo, 3 different proxies with different caveats for how they're reflecting changes in rainfall. In northern Papua New Guinea, this is from looking at changes in runoff and sediment input to a site offshore through the ratio of titanium to calcium in a core. So the Borneo stalagmite record looking at changes in precipitation isotopes as an indicator of rainfall. And this is from southeastern Papua New Guinea looking at the neodymium to calcium ratio and plankton foraminifera, kind of indicating more of a chemical weathering and erosion signal here. And so what we see, at least in their power spectra, all 3 of these records, regardless of proxy and their precise location in the warm pool, show significant power at the precession timescale at 23 kiloyear cycle. And then 2 of the 3 indicate obliquity may exerts an influence on rainfall in this part of the world as well. Notably absent from all 3 of these is glacial interglacial or eccentricity signal. And this is in part, we're kind of wondering if some of these records are quite short. They have maybe 1, possibly 2 glacial interglacial cycles as record length, possibly preventing the signal of kind of glacial interglacial change from popping up in these power spectra, or is there really no significant impact on rainfall here? So that is some of the questions we'll kind of seek to answer here. All right, but looking at these previous records, we see a clear influence of precession, indicating a strong impact of local insolation and driving changes in rainfall in this region. Now there's still questions as to how exactly it happens. Does precession lead to kind of north-south shifts in the zone of rainfall, expansion, contraction, or some other mechanism? And then the role of extratropical forcing. Not all the records show obliquity forcing. None of them show eccentricity. What is the role of extratropical changes in the climate system on rainfall here? And those are some of the things we'll seek to explore by looking at a record from this part of the world that extends those records of rainfall further back in time. So that was one of the many objectives of IRDP Expedition 363 that went back in 2016 now, quite a while ago at this stage. On that cruise, so we took many sites. I'll actually talk about this site here, previous record from 1483 that was recently published by Zhang et al. And Ann Holborn's group. But I'll be talking about this site here, U1486, off the north coast of Papua New Guinea. And this site here will provide a really amazing record of changes in rainfall and runoff in the kind of the heart of the warm pool region. And this is lying just off the north coast of Papua New Guinea, and you can see this is kind of that view looking back towards shore from these sites here. And you can see, this is a very typical view of Papua New Guinea of the rainfall right over those very high mountains with lots of fresh material there. Lots of rainfall, lots of erosion that we can detect offshore. All right, so I'll talk a little bit more in detail on this site because it'll form the basis of the talk today. So it's located, this is a zoom in on what we were just looking at. So this is northern Papua New Guinea. You can see site 1486 off the north coast of that. Offshore of these two rivers, the Sepik and the Ramu River, is our major river systems in Papua New Guinea that are draining the highlands of this region. And so it was recovered at 1332 meters water depth. The bottom of the core is about 2.7 million years ago. And because of where it's located offshore here, these river systems bring lots of terrigenous material via runoff to this core site. Our site is composed of a combination of biogenic carbonates, about 60% of the core composition are carbonates, and then the rest is terrigenous and volcanic material. And you can see if you look in satellite images, this is basically that same view we were just looking at in that map. You can see these huge sediment plumes of sediment kind of making their way offshore of the north coast of Papua New Guinea. And what we'll, in this part of the world, we're in the tropics, it is wet here pretty much all year round, but there is a significant seasonal cycle in this part of the world. It's wetter here during austral summer, upwards of 300 millimeters of rainfall per month, and it's drier in boreal summer in this part of the world. And this is kind of following the north to south migration of the ITCZ. We're located a bit south of the equator here, and therefore we have more rainfall when the ITCZ is in its southernmost location across the year. All right, and so we're going to be looking at changes in the amount of terrestrial material that make their way to our core site as an indicator of rainfall, moving sediment from onshore offshore with greater amounts of these terrestrial materials, likely indicating greater amounts of rainfall and runoff. And we'll look at three different elements. We'll look at titanium, potassium, and iron. And these are measured using X-ray fluorescence core scanning. We scanned about every 2 centimeters, so that's about every 350 years. We scanned 28 different elements. There's a whole treasure trove of data here that we still, beyond just looking at these 3 elements, and I'm sure that will produce interesting things down the line as well. We calibrated these data from counts per second into weight percent through a flux fusion method of a handful of samples throughout the core. The age depth model for this core is constrained in a couple ways. The upper 400 meters, where we actually use the XRF core scanning to match to a nearby site that had a well-constrained age model from radiocarbon as well as benthic oxygen isotopes. So this is this previously published record from Tachikawa et al. In blue, the log titanium to calcium ratio. And this is our site, the same thing, log titanium to calcium. And we use that to kind of map out the age model for the upper section of our core. And then of course, our site goes back much further in time to about 2.7 million years ago. And we constructed an age model using benthic delitino of benthic foraminifer, a combination of Cibicidoides mundulus and Planiolana willistorfi. And just to reassure you that our age model is more than sufficient for orbital scale variability. Just kind of collapse those, and you can see it's quite a nice match to the LOR4 benthic stack. All right, so we'll look now at our records of these terrigenous elements that we'll use to infer changes in rainfall over Papua New Guinea. And we'll just start by looking at the long-term record of these 3 elements. So on the bottom, this is the benthic oxygen isotope record, just to kind of orient you in terms of where we are in time and kind of the general climatic setting. Then we have potassium here in blue, iron, and titanium. And these are all shown on the carbonate-free basis to correct for the impact of dilution by biogenic carbonates. And what you can see, what kind of immediately pops out at you is the kind of long-term trend of decreases in both iron and titanium before they stabilize during the late Pleistocene period. And this really reflects a long-term change that was observed shipboard when we were at sea. We observed a long-term decrease in volcanogenic sediments at our site. These are the core photos. You can see that this is really reflected in the color as well. And yeah, we see a decrease in the amount of volcanic material. What you'll notice is that the potassium does not show this change, and it's likely that this volcanogenic material was kind of a low potassium mafic type chemistry. So we'll come back to that a bit later, but for now we'll look in the later part, the late Pleistocene period, where we don't need to kind of worry about this potential complication of changes in the source material that's being eroded off of Papua New Guinea. And over this time interval, regardless of what proxy you look at, which element, they are all showing basically the same thing in terms of their variability at orbital timescales over this period. And just to demonstrate this, so this is the coherence between iron and potassium over the last 800,000 years, and as well as their phase. And so basically at each of the key orbital periodicities, precession, obliquity, and eccentricity, we see high coherence between these proxies and pretty much no phase difference between them. So they're really recording the same thing. You can do this also with titanium, and it's basically the same story. So for the most part, these elements are behaving the same over the late Pleistocene in response to changes in orbital forcing. So for now, we'll use iron to look at the orbital response at our core site, and but know that this is consistent with the other two proxies for the most part. All right, so this is the power spectra for the last 800,000 years at site 1486. We infer increases in iron at our core site to reflect greater rainfall over Papua New Guinea, greater erosive power and movement of that terrigenous material offshore to where it eventually lies at 1486. And when we look at the power spectra, we see precession, 23 and 19 kiloyears showing up here, as well as obliquity and a very strong 100 kiloyear cycle. Also note that there are some heterodynes that have been seen in other rainfall records in and around this region. And we'll kind of follow on some of previous work from Zhang et al. Comparing their record at the southern margin along the northern coast of Australia to sites in the heart of the worm pool and the northern margin using the cave composite speleothem record. And we'll just look at these in spectral space. And so here, just looking at 1483, this is off the Australian margin. This is the cave composite record we're all familiar with, showing this very strong and pretty much only power at precession. Along Australia, we see both precession, obliquity, 100,000, and also some of these heterodyne peaks as well. And just for a direct comparison, now I'll add our power spectra here, and you can see that all of the records show power at precession. We see obliquity and particularly strong as 100 kiloyear at 1486 off of Papua New Guinea, our site, and off of Australia here. And in fact, what's the power spectra for are these two records from Papua New Guinea and Australia are remarkably similar, even at these kind of non-primary peaks in orbital forcing. All right, so but let's look in terms of kind of phasing response, and so we can look at in the time domain first. So we're going now just back to 400,000 years because these records are not quite as long. So this is the record from the Australian margin. This is also an XRF record looking at input of terrigenous material off North Australia. Up here means more rainfall at this location, at the southern margin of the ITCZ range. Up here, this is our Papua New Guinea record. This is the iron on the carbonate-free basis. Up here is more rainfall in Papua New Guinea. This is the cave record plotted. So up is theoretically more rainfall in this part of the world. And then on the top here, I've plotted Southern Hemisphere summer insolation in January at 3 degrees south. So we would expect that this would lead to greater rainfall at our core site, as it is located just south of the equator. And what you can see is that in general, when there is greater summer insolation over our core site, we tend to see a peak in iron, indicating a peak in sediment transport and rainfall over Papua New Guinea. This is, of course, out of phase with what is observed in the Speleothem delatino record. It is also out of phase with what is going on down here on the Australian margin. I know these wiggly lines can be hard to look at sometimes. So there we go. So I kind of just collapsed just the cave monsoon record and our record here. I flipped the axis for the cave record. So down is now more rainfall indicated by that record. And you can see they map onto each other quite well at the precession band. Yeah, we could move that up there too, and you could see a similar relationship. Some of you might be more comfortable looking at this in terms of the phase wheel. So at the top here, this is precession minima, indicating maximum summer insolation in the northern hemisphere. And this has been shown before for the cave record as well as the Australian monsoon record. These are lagging precession minimum by about 3 kiloyears. And then we can plot the phase relationship of our proxies here in Papua New Guinea. And these are for all three now of the different elements. They have slightly different lag to the precession forcing, but they're also on average within uncertainty about a 3 kiloyear lag from precession maximum. Sorry, that should be P max there. All right. So these appear to be basically out of phase in the heart of the warm pool and with those records that are on the margins. And this was demonstrated again by Zhang et al. By comparing the southern margin site to the cave sites to this record here in the very southern part of Papua New Guinea. This is the neodymium calcium record. I showed the power spectra for that earlier in this talk, but it has a very similar phase relationship with a totally different proxy. This is neodymium to calcium in foraminifera coming from the southern part of Papua New Guinea, and showing the same phase relationship to the precession forcing. So this really, our site and the record here supports the interpretation of Zhang et al. That there's an antiphase relationship between sites at the ITCZ margins and those in the meteorological center. And our site is very much within the heart of this region, and so provides a lot of support for that interpretation. And so that spatial variability suggests that instead of kind of a mean shift in the north-south position of the ITCZ, what we're actually seeing is an expansion or a contraction of the ITCZ in response to precession forcing. And so, yeah, so it doesn't look like this kind of north-south shift, but rather expansion and contraction as demonstrated here. All right, but why might this be the case? An interpretation was provided in a paper by Singarai et al. In 2017. Essentially, what they demonstrated in their modeling results that we can kind of walk through here. So this is precession insolation change between precession minima and maximum across the year and across all latitudes. And so basically at precession minima, we have more heating in the northern hemisphere. And so the ITCZ is drawn further north. That's pretty straightforward. When What happens in austral summer is a little bit less intuitive because the southern hemisphere cools more, or it gets has a larger insolation change in terms of less insolation than the northern hemisphere, which you might expect just would keep the ITCZ from moving too far south and leading to a mean shift towards the north. But instead, basically what they demonstrated was that because you have cooling, or you have less insolation coming in the southern hemisphere, you also have less in the northern hemisphere. And even though the magnitude is less in the northern hemisphere, because you have more land masses, this causes the northern hemisphere still to cool more than the southern hemisphere, allowing the ITCZ to move further into the southern hemisphere. And so then you have the ITCZ moving further north in boreal summer, further south in austral summer, and this leads to a mean expansion in the ITCZ at precession minimum, and vice versa at maximum. But the real kind of advantage of our record relative to what's been done thus far is that it does extend significantly further back in time. And we can look at this, and we'll use, for now, we'll be looking at potassium because there's no significant change in the source region of where potassium is coming from across the full range of our record, unlike what we see in the iron and titanium. And so we can, this is a coherence diagram between precession now and potassium over the 1.2 to 2.3 million years, so before the MPT. And we see that potassium is coherent with precession, and the phase lag is pretty much the exact same it was in the post-MPT world. So it's still about 2.3, about 3 kiloyear lagged from precession maximum. This is the same as we saw in the post-MPT world. And what this tells us is that the response to precession has not really changed over the full time interval that we have our core site. So this antiphase relationship that we see over the last 400,000 years, where we have records at the southern and northern margins directly to compare to, that this appears, given that the phase relationship of rainfall here doesn't change, suggesting the mechanism hasn't changed. This is probably what's been happening continuously over at least the last 2.3 million years. All right. So precession drives an expansion and contraction of the tropical rain belt by its impact on the inner hemisphere temperature gradient, or the precession forcing impacting the two hemispheres in different ways because of the different land masses. And then the precession phase is stable across the mid-Pleistocene transition, suggesting that the same dynamics are at play across this entire time interval. All right, so that was precession, but of course there's our responses in many of these rainfall records at the obliquity timescale as well. So we'll look in a little bit more at this, and we'll kind of follow the lead of this previous publication by looking at another record of rainfall in China, the LUS record of strontium calcium, which shows a strong obliquity response that you don't see in the cave record. So for this, we'll use this record to compare to. All right, and so we can do the same thing, and it was shown previously that the amount rainfall at the northern margin of the ITCZ and the southern margin of the ITCZ at the obliquity timescale are out of phase with one another. And this is unlike the precession response, in which these two regions were in phase with one another. And so this suggests that the response, they suggested from this that the ITCZ, instead of an expansion contraction modality, was changing its mean position in a north-south manner. And we can also plot how the phase of our record here, and you can see it's neither in or out of phase with either of these records. And this suggests to us that the control on rainfall at the obliquity timescale at our site in the heart of the warm pool region is not related to a north-south shift. However, this does not suggest that this is not happening. It's just that here in the heart of the warm pool, a north-south shift is likely to have a pretty limited impact on rainfall. It's not going to matter if it shifts a little bit further south or north because we're really settled here in the center. So we're still working on the precise mechanism for driving rainfall at our site at the obliquity timescale, but it's not inconsistent with what has been shown previously of a north-south migration being kind of the modality at the obliquity band. All right, so yeah, so obliquity, we see this north-south asymmetry, and at the precession band, we see an expansion and contraction. And it's somewhat, so the precession influence on expansion and contraction was explained in part because of interhemispheric temperature gradients. But of course, obliquity is also often thought about as a similar impact of changes in the pole to equator temperature gradient. But there are, of course, really important differences between these two changes, or the forcing of these two different orbital frequencies. And so this is the same plot we looked at before, showing the difference in the change in insolation between precession minima and maxima. Down here, we have obliquity minimum and maxima changes. And so just a couple of things to highlight, of course, are that the precession forcing is seasonally asymmetric, but latitudinally symmetric, whereas obliquity forcing is seasonally symmetric and latitudinally asymmetric. So there are really important differences in kind of the flavor of temperature gradients produced by these two different orbital forcings that lead to these differences in the precipitation response and the response of the ITCZ. All right, so at the obliquity band, our results are consistent with a north-south migration in the ITCZ. It's not what's driving variations in rainfall in the heart of the warm pool, but it doesn't discount this interpretation for sites at the margin. All right, and finally, we'll take a closer look at this very strong 100 kiloyear band that we see in our record, but also off of Northern Australia and in China, at least in the strontium calcium loss record. And one of the first thing that's puzzling is that we see this very strong 100 kiloyear band at our site. But if you remember back to these 3 prior studies from the warm pool region, none of these showed a 100 kiloyear cycle in their power spectra. I mean, maybe for some of these, it's just, don't have enough cycles to get a robust signal in the spectral domain. But we would certainly expect to see that in this power spectra covering 4 glacial interglacial cycles. And it's using extra F core scanning from a site very, very close to ours. In fact, this is the site we used to constrain our age model over the last 400,000 years. So the lack of coherence between the spectra for this record with ours was a little bit concerning. And so I think there is a good explanation. And so I'll just walk you through that pretty quickly. So this is our site here, 1486, the MDO 52920. This is the record from Tachikawa et al. For this power spectra you see here. It's a bit closer to the northern margin of Papua New Guinea than ours. It has about half the amount of calcium carbonate that ours does, being a little bit further away. So more treacherous material here, obviously, given that it's closer. All right, but basically, you can see here, we see 4123 from this record of the log titanium to calcium, and we see 141 in precession at our record. Now this is coming from the iron on the carbonate-free basis. So the first thing to do is, this is in log titanium to calcium. We don't do the ratio to calcium because there's so much more carbonate at our site that it has a really big impact on the dilution from the calcium, has a big impact on the variability. But what we can do is we can compare at least titanium on the carbonate-free basis to the titanium calcium record at this site. And this is our titanium carbonate-free basis over the last 400,000 years, so being consistent with the record length of this previously published record. And what you see is that actually, when you look at the titanium rather than the iron, and just over the last 400,000 years, you don't see a 100,000-year cycle. So at the very least, we're confident that our sites are reflecting the same thing in these, which is pretty comforting. However, it's not, it wasn't an artifact even of looking at like the last 800,000 years in the iron. If we look at the last 400,000 years in iron, we still see a 100 kiloyear cycle. And same in the potassium. So this is actually kind of a result of looking at different elements as being representative of runoff coming from Papua New Guinea. All right, so this, I think the fact that all of our Triginous proxies are not consistent at the eccentricity band gives us a little bit of pause in terms of interpreting this as a direct proxy of rainfall. This is very different than what we see at the Precession and Obliquity when all three proxies are showing roughly the same thing. All right, so here I'll just show in kind of the time domain, the iron calcium-free basis, showing these strong 100,000-year cycles with the benthic delete-no record in black. And so what you can see is that during max glacial periods, essentially we see less iron making its way to our core site. So this is not reflecting changes in the position of where our site is relative to the shore because of changes in sea level. Remember the shelf off of northern Papua New Guinea is very, very narrow. So it's possible then that this could be reflecting a true climate signal of less iron, less rainfall, less delivery to our core site, and drier during glacial periods, which would be consistent with a lot of modeling and other work from this region. But given some of the discrepancies between our various proxy indicators, I think we also need to consider that there are non-hydroclimate things at play here, and potentially, as shown by Peter Cliff and discussed in last week's monsoon seminar, changes in sediment storage on the shelf could be impacting this. Even though it is narrow, potentially we have more sediment being stored on the northern Papua New Guinea shelf during glacials, and kind of starving the offshore site of sediment during these times. So all of these are possibilities. So to dig a little bit deeper into this, we can compare our site 1486, which is further offshore, to site 1485, which is right here on the slope. To give you a little bit better perspective, these are those two sites, so 1485, 1486, 1485, 1486. And you can see 85 is right on the slope off the shelf, and then it's 86 is further offshore here. All right, so we'll look at the record. So we also did XRF core scanning at site 1485, closer to shore. And this goes back about 400,000 years. On the orange, this is the log iron to calcium. We can do the ratio here because the calcium contribution is very, very small and unlikely to have a significant impact on the changes from iron. Terrigenous material is the dominant component of this site. And I flipped this axis, so down is more iron, so more terrigenous material at this site on the slope. And then I'm plotting this with the LR4 delete-no record, but the delta, so basically looking at change in benthic delete-no as kind of a proxy for rates of sea level rise and fall. So down in terms of how I've calculated this represents a drop in sea level, and up represents a rise in sea level, and the kind of magnitude tells you about the rates. And what we can see is that in large part, it appears that our record at site 1485 on the slope is regulated by changes by rates of sea level rise and fall. So we see more iron delivery to 1485, in sync with periods of very rapid sea level drop, and less iron delivery to our site when we have periods of sea level rise. And just to kind of clean this up a little bit so it's easier to see, I did a 100 kiloyear filter of both the iron record and the LRO4, the Delta LRO4 record. And then I flipped the iron. So up on this one is more iron delivery to our site, and down for the blue is a sea level drop. And so basically we see max iron delivery to 1485 when we see max sea level rise, and then greater iron delivery to 1485 when we see a sea level drop. So this seems to be largely controlled by changes in sea level, at least close to the shelf. But this is not the case actually at 1486, which is further offshore. So you kind of, the bathymetry drops and then it rises again, and that's where 1486 is. So instead of being in line, the iron supply being in line with changes in sea level rise and fall, it's in line with kind of maximum in the Del 18O benthic record. So we see essentially that we get the maximum iron delivery to 1486. So that's up in both of these diagrams, occurring with ice volume minimum, and we see minimum iron delivery during ice volume maxima. And so this might suggest that unlike 1485, perhaps 1486 is more related to changes in climate than just, well, the 1485 is related to climate, but the sediment transport is related to sea level, whereas the sediment transport to this site may be related to changes in hydroclimate. But given the fact that the response of our three proxies are not consistent, we're kind of hesitant to be too confident in any of this yet, and it needs a little bit more work. So we clearly see that sea level drives changes in terrestrial input to sites that are closer to shore on the slope at 100 kiloyear cycle. But it's not yet clear if the 100 kiloyear cycle we see at 1486 is a hydroclimate response or some combination of other processes. So stay tuned on that front. All right, and with that, I'll kind of end there and highlight kind of the general responses we see at the different orbital frequencies. So at Obliquity, our data are supportive of a north-south shift in the intertropical convergence zone. At the Precession timescale, our data are more consistent with an expansion and contraction dynamic. And at the 100,000 year cycle, glacial, interglacial cycles, this may be related to kind of land exposure and leading to a drying during glacial periods or impacts of ice volume. But we're still kind of trying to figure out whether or not there might be kind of non-hydroclimate processes at play here. And I'll also note that although it has been described before that the precession response is kind of expansion contraction over the last 400,000 years, our record suggests that this is kind of the modus operandi across the last 2.3 million years as well. So it's been operating for a long time. And with that, I'll end there and take any questions that might have arisen during the talk. Thanks.
Excellent talk, Samantha. Thank you so much. So I see that we've already gotten a couple of questions here in the chat. The first question is by Steve Clemens. Would you like to ask your question?
Hi,
or elaborate?
Sure, thank you. That was a great talk, Sam.
Thank you.
I'm wondering why it was necessary, maybe not necessary, I'm wondering why you used the strontium calcium record to compare from LUS to compare with your obliquity signal, but the cave Del 18 record to compare with your precession signal. You know, almost all of the LUS records that purport to track rainfall have 141 and 23 in them. So why not choose one that is more similar to your 1486 results in that regard?
Yeah, no, it's a good point, and actually something I've been thinking a lot about in the days coming up to this presentation. And I should be looking at both of those is the answer to that question. And as I was kind of doing the practice talks, I was thinking that it might be somewhat arbitrary to not include, to kind of pick and choose which one of those records. So I guess the short answer is that I've kind of come to that realization myself, that I didn't quite get to it before this this talk. So yeah, it's something I should do. And I think that there are pretty significant differences as well in terms of the precession phase between the cave and that record. And so including both of those would be important.
Using the LUS records are difficult as well because the age models aren't constrained in the same way that, you know, either the cave or your records are. So I mean, that's an issue as well. But thank you.
That's true. Okay, thank you for your comment.
So we have a second question by Peter Clift. Peter, would you like to read out your question and elaborate?
Yeah, sure. So I guess what I was intrigued with the initial record you showed us sort of a decrease in iron and titanium, and I wondered, well, what was doing that? Do you think that's the tectonics of New Guinea? Because that's not really what you see in most systems, is it? So I mean, it's a little bit unusual. I mean, it's sort of, I know you then focus on the flat bit, but presumably that doesn't indicate a long-term decrease in monsoon rain strength at that time.
Yeah, no, I don't think that's the case. I think basically what we're seeing is a long-term, well, basically that there was probably tectonics and greater volcanic material supplied in the early part of this record. And that fresh volcanic material probably got eroded by about the mid-Pleistocene transition period.
Is that an important distinction between volcanic versus, say, other siliciclastic terrestrial material?
Yeah, I think it is. Well, for example, I'm pretty sure it is a fairly mafic end member because we don't see that being reflected in the potassium record. So this kind of seems like whatever is supplying the potassium is not changing a whole lot in its distribution. I mean, I guess either you have a lot more volcanic material supplied to the surface, indicating a huge increase in volcanic activity in the early part of this record, or I guess another explanation could be that your rivers or rainfall regions supplying the sediment could have changed, but I think that's probably less likely given what we see.
I did wonder if it could be caused just by like drainage evolution, if the river mouth was moving around.
Yeah, so that's looking at like changes in provenance, and I have a student looking now at kind of the modern distribution of different chemical signatures across different parts of Papua New Guinea, and I don't think we can align this change with what we see in the modern system, but it could have obviously been much different back in time. So that is definitely something I know Yair will be working, and probably some of his students will continue to kind of work on what exactly your question, what this means, and did that have an impact in and of itself in terms of weathering on the climate system. But yeah, I haven't delved too far down that one. Yeah.
Thank you, Samantha.
Thanks.
Okay, we have a third question by Antje Volker. I apologize if I mispronounced your name. Would you like to read out your question and add a little bit more?
Well, you actually pronounced my name pretty well. This is actually a little bit more like a comment. Mm-hmm. It's just like, don't forget to play with the frequency filtering to get an idea where your signals might come in. it's like I was thinking for all of them, but your discussion of the 100 kiloyears, so the eccentricity, it might really be helpful to see where you get the higher amplitudes in your record.
Yeah, so I didn't show that here. I have played around with doing that, and basically you see the amplitude of the 100 kiloyear cycle in our record. It doesn't necessarily track the eccentricity 100, the amplitude of the eccentricity cycle, but what it does map onto is the amplitude. Like if you did a 100 kiloyear filter of the LRO4. And so it does kind of map in terms of the amplitude of the 100 kiloyear cycle in our record and the 100 kiloyear cycle in the LRO4. It kind of maps onto the magnitude of ice volume. So that is a signal in there, but I didn't talk about that today, but good point.
No, it was also to kind of show that it's not really like a double obliquity elongated, or like it's like really then a true 100 kiloyear cycle signal or something like this.
Yeah, it does seem to be the case, at least in the later part of the record.
Okay, good, thanks.
Mm-hmm.
And then we have another question here by Mark Yu, kind of going back to a little bit about this titanium. Mark, would you like to read out your question and elaborate at all?
Yeah, sure. Great talk, Sam. Just I have a quick question. It might be fairly simple, but so could the iron and the titanium be aeolian derived from Australia or other deserts? And could you be seeing a record of aridity along with hydroclimate?
Yeah, so I don't think so. And that based on, in part from just looking at the cores themselves. And so you can see that the sediment is changing as you go down core, and when you start to see this ramp up of iron and titanium, you can see in the core itself this volcanic material. It's fairly, in fact, coarse grained. And actually, if you'll note, we stopped scanning at 2.3 million years, but the core extends to 2.7, and it's just that there was so much sharp volcanogenic material in the deeper part that it kept piercing the film, making scanning not possible. So I think it's pretty clear where that signal is coming from, just kind of based on looking at the cores themselves. But I think the other reason that it's probably not dust is that, I mean, I guess things can change back in time, but it's a pretty wet place, and I think it's probably been pretty wet over this time interval, and I expect that the dust probably gets rained out before it makes it here. And then there's been some studies looking at like core top sediment, trying to look at the kind of possible input of dust right now, and they don't see a huge impact of dust or a huge contribution of dust to the core top sediment at present day. So yeah, so I think probably unlikely, but I can't 100% rule it out, I guess. Yeah. Thanks, Mark.
We have another comment by Yair Rosenthal. So if you could share it, please.
Yeah, a few things. Peter, once your question about tectonic and Sam mentioned, and I think about that, it's not just that the iron and titanium are higher in the lower part of the record, but you see progressively more and more ash layer and eruption. I mean, the shreds are really sharp. So those are real in situ deposition. And we know some of them are subaerial, some of them submarine. So that's a totally different story. And at the bottom, we stopped drilling because we hit a really basaltic basement. So this whole area was interestingly very volcanically active. Seems to be at least through the early Pleistocene. On the other question, is tectonic or not, and the 100 kiloyear, just to remind also Sam, I was reminded that Ivano Ayalo in the paper that we did in 2019 now, so a while ago. We basically see he reports what he thinks major tectonic changes that has to do a lot with movement on the strike fault that we have there. And they express themselves very well at around 400,000 years, if I remember, at 1485, the core that is very close to the margin. But we don't see much of that in 1486. So the sea level tectonics, all the local effects seems to be very evident on the margin, and to some extent are filtered essentially in the distal site of 1486. So we probably, Sam, you're right, that you see there much more of precipitation signal. It still doesn't explain the discrepancy between titanium and iron and potassium, which is an interesting and may have to do with drainage system. Yeah. I have a question for Tara. I mean, could that be related to grain size changes? I mean, that's your expertise, so that would.
One of them, potentially. Although I'm glad that you commented about the geochemical changes up core, along with the increased what sounds like tephra layers in there, because I was wondering a little bit like what Peter had commented on about whether it was like a tectonic signal in terms of like I guess subduction zone input for magmatism, but because you see that geochemical change as well, it changes the story a little bit. In terms of, I don't know, grain size, I mean, that would be one thing that you could just easily look at the core. I feel like at least some, or maybe, I don't know if the shipboard data would have that. And then maybe some of the other elements as well that you collected with the core scanner, especially things like, I don't know if you've got aluminum at least, or other types of like coarse versus clay-sized proxies. Oh, here we have some more comments here. Here's another from Pallavi Anand. I don't know if you wanted to add more to that. She's in the chat here. Iron could also be from multiple sources, I think is what she mentioned. And then Peter, you also have another comment down here about the volcanic signal was eroded from the ophiolite and arc units and not tephra. Interesting. Well, I mean, I guess in that, especially if the potassium's now changing.
Well, I can answer it without the guessing, and Sam. I mean, you have the northern side of Papua New Guinea are lifted ophiolite, so we are getting their erosion like crazy of those things. In terms of tectonic or volcanic, I mean, they are coupled. But if you're talking just about lifting, uplift, or things like that, we know that there were eruptions. The tephra is all over, so the signature. Yeah, and Pallavi, we are thinking along this line of hi, Pallavi.
Yeah.
You do have their drainage that's coming from felsic and also from mafic, ophiolite, and so. Yeah, there might be a mixture that is changing.
Yeah, but also I just wanted to add one thing, I mean, how productive is the site? I don't know, but you could have pyrites and things that could contribute some of your iron as well. So just thinking about the sediment composition could be quite important, I think. I don't know, but I don't know the site, so just a thought.
Yeah.
Iron is the force bonded, element on Earth. Pyrites is just a second fiddler there, right? The detritus bring in tons. It's hard for me to see. We work in Sam is leading a project in Chile. Even there, I don't think pyrite is. I mean, it's important for many things, but not this signal. That's my view, but I might be wrong.
Yeah, I guess then it would only be behaving differently at some frequencies, and which, I mean, I guess it's possible with productivity changing at some rather than others, but yeah, there's just so much supply of it that it's hard to, I think
But there
that's
are
just the biggest
changes
signal.
in reducing. I mean, we have it from the NGR and Vera, who worked Lawson on that. We do see changes in the uranium, so it's probably changing.
Okay.
Redox condition. Yeah, I think we see that of 1445 of Bay of Bengal. So I just thought worth looking into it. Yeah. But also you could do you can look at your XRF data and it's very scatter diagram will tell you whether it's a single source or multiple source very clearly, actually.
Yeah.
Just like a rough and quick measure, really, I think.
Yeah. Thank you.
Well, I think that about wraps it up for today. So let's again put our hands together for this excellent talk by Samantha. It gave us all a lot of food for thought and is absolutely data rich. So it's really great to see all the hard work of you and your team. And so before everybody runs away, please make sure to tune in next week for our Schedule B speaker, who's going to be Aaron D. Singh next week on September 22nd. So just remember to check your emails for any announcements that are sent to you. And if you'd like to be added to the email list, please email myself, Liviu, or Peter, and we'll add you to the list. But otherwise, have a lovely rest of your day, and we'll see everybody again next week.
Thanks, everybody.
Bye.